sharing later. Yeah, but the event destruction.
Okay, I think we'll be starting soon. We still have people joining in. I think it's, but let's give people 1 or 2 minutes, but then we will start. I'm already live, so that part I don't have to do, but I need to resume recording once we start. So I'll keep it here. We will start in 1 minute. Okay, everyone, let's start. Welcome to Hot in Networking track. Today we have three talks: network programming, MADINAS, and intent-based networking (IBN). Three really great talks from hottest topic in networking at standards body and outside as well. So we are really grateful for three really great technologists to come and speak to us. Looking forward to this. uh, Request for audience, please use Q&A in your Zoom webinar to ask your questions by writing it down clearly. The questions will be visible to all and audience can upvote. The panelist can also answer the question by writing it text or even marking that they would like to answer the question. And if you wish to speak, you can put it in text that you would like to be unmuted, and we can do that as well. Whenever you are not speaking, please mute yourself. I think we know the Zoom etiquettes now. We have been doing this all year now. We have a Zoom chat, so please use that to continue to message folks during the meeting. But use Q&A when you have a question that you need to ask the speaker. We have a Zoom meeting also set up, that is to socialize outside of this webinar. So this is available both pre and post events. People come in, say hi to each other. We met seeing each other's faces. So anybody who's interested in some networking aspects, please use the link at our program page where you will find the Zoom meeting link, and that's available both pre and post events on all days. Uh, we need to thank our sponsors. They have been helping us run this event for all of 4 years that we have been doing it. Internet Society has supported us for all 4 years. Juniper has supported us for all 3 years. So we are really grateful for their continued support, and they continue to see value in what we do. So thank you for them. Since this is brought to you by two organizations, IISOC and INTC, we have our IETF Community India mailing list on IETF. So we are thankful for IETF to giving us the space. Please join if you are interested in activities that are happening in India. We have a quite active WhatsApp group. I will put all these links in the chat window once I'm done. So you have these links handy. We are on LinkedIn, Twitter, all the usual spaces as well. For INTC, we have you can contact us using the link there, and then you will be added into a list where we will notify you of our upcoming webinars and workshops and all the things that we have been doing. We have been doing this whole of this year. We plan to continue in 2021. So if you found those webinars interesting, please stay in touch so that we can keep you informed. So let's start with our first talk, which is network programming by Jim Guichard. Jim is the Distinguished Engineer and Technical VP at IP Protocol Innovation and Standardization at FutureWay, which is the Huawei US arm. He has 25 years of industry experience, expertise in MPLS, routing, L3 VPN, SDN, segment routing, service version chaining, really a routing experts in all these areas. Around 150 plus patents. He's written books. Has been in the industry for the long time and has currently co-chairs Spring and SFC working group at ITF. So I have been communicating with Jim since he's joined FutureWay and earlier. I'm always amazed at his technical depth and knowledge that he has. So we are really looking forward to this next talk for him. So off to you, Jim. I'll stop my share and you can share.
Thank you, Dhruv. Let me just bring up some slides here. Can you hear me okay?
Yes, Jim. Loud and clear.
Okay, well, hello, everybody. Morning, evening, afternoon, not quite sure. It's late in the evening here, but I guess morning where most people are. I'm going to spend the next probably 30 minutes or so talking about a technology that I've personally been working on for a number of years now. And a lot of the work in the Spring Working Group, which I co-chair, is aimed towards this particular topic. I'm going to try and introduce SRv6, if you're not familiar with SRv6, I can give you a very brief overview. But what I'm really interested in is going one step further, which is the concept of using SRv6 as a way of programming the network to do things that are kind of difficult to do in the environment that we have today. So that's what I'm going to try and achieve. Hopefully we'll have some time at the end if you have any questions. I'll try to see when questions come up, but it's a little bit difficult to see on this screen when the hands go up, unless somebody interrupts me. But if not, I'll save the questions until the end. So a little bit of background to get us to SRv6 and why we're here. So we've kind of gone through this protocol evolution, and I've been involved in most of this over the years. So we started off really talking about just reachability. That was really what the network was for. And then we moved into connectivity and services, and we started to see things like VoIP and IPTV, VPNs and so forth come onto the network, and an increase in protocols. And in the last few years, what we've tried to start to look at is simplification of the network, because there's so many protocols out there that we've kind of developed over the years that are running together, and we want to try and remove things that we don't need and only keep what we need, and then try and grow on top of that to take care of the requirements that we're seeing coming out from things like 5G. The other area that we're very interested in is this concept of programming, and I'll introduce it shortly in a few slides, but the idea of being able to use the network to do more things than just connectivity and traffic steering. What we want to be able to do is some more fancy things and some things that actually make the network much more useful to us. So in order to do this network evolution, we need a starting point. And really the starting point from my perspective was IPv4 with MPLS on top. And we spent many years working on MPLS. I personally worked on the VPN aspects of MPLS, although I'm familiar with all of the other aspects. But as you can see from this picture, what we've kind of ended up with is multiple protocols in the network. So we've got the interior gateway protocols, whether it be OSPF or ISIS running. We've got some border gateway protocol. We've got LDP, which is a protocol that allows us to distribute MPLS labels. We might have some RSVP-TE, which is another MPLS technology that allows us to do some traffic steering in the network. And we might have fast reroute as well, which is a protection mechanism in an MPLS network. On top of this, we've got multiple services running. So we've got the basic shortest path algorithm for the routing protocols. We've got traffic engineering, as I mentioned, some fast reroute protection, some VPNs running across there, whether they be layer 2, layer 3 VPNs or possibly even both. And the upshot of that is that we end up with a lot of state in the network to support all of these services and all of these particular protocols. So what we wanted to try and do is actually remove any state that's really unnecessary for us, and also any protocols that are unnecessary. So that's where the simplification comes in. So what we've tried to do is move away from MPLS in the forwarding plane, which allows us to remove things like label distribution protocol and all of the traffic engineering and fast reroute mechanisms from RSVP-TE. And in the core of the network, we may even be able to remove BGP and just keep that on the edges. So that's kind of where we're going to. And as you can see, it really helps us to really remove protocols that we don't need, remove state that we don't need, and basically simplify the network. So once we've got that starting point, as we evolve, we see that there are new protocol requirements that are coming in, primarily driven by things like 5G. So first and foremost was the simplification in the deployment of the network protocols. We already talked about that. There's also a push to have intelligence just at the edge, and extended end-to-end as well, with some kind of edge and cloud integration. The implication of that is that we probably need an end-to-end protocol or transport protocol, unified transport protocol, that we can run ideally all the way from the handset into the data center. At least that's the vision. We also probably require intelligence in the network, and that's kind of a controversial discussion in the IETF. There are people, purists, that think we shouldn't have intelligence in the network. There are people like me that think we do, we should have. And by having that intelligence, we can really support some new functionality that allows us to drive some of the services, the new services that we want to put onto the network. And those services, what we're seeing, are really decomposed. And this is an area that I've spent a lot of time working on, which is the service chaining, which is basically the ability to automate the service composition through chaining. And that the idea here is that these service elements, and there may be more than one, are chained together to form a service, but those particular elements could be anywhere in the network. And we want to be able to do that in an automated fashion. And that's basically where all this service chaining work is, and the lifecycle management of that. Obviously, there's been a move towards virtualization. So we've got environments with both virtual infrastructure as well as physical network infrastructure, the routers and the switches and so forth. And a lot of a push to have policy distributed through the network that allows us to potentially identify the particular characteristics that a particular user is going to get on the network. To be able to support those kinds of things, we need to have awareness of context in the traffic flows. We need to have be able to identify or have identity, I should say, with policy. So who you are, what you are, where you are, those types of things. And depending on who you are, where you are, and what you are, might depend on what policy gets applied. So for example, if Jim's in his home office accessing some kind of application, then policy A might be applicable. Whereas if I'm in my corporate office, then a different policy might apply. The network intelligence in the network, which I already mentioned, supported through metadata. We'll talk a little bit more about that. A closed loop telemetry, so we can actually dynamically move things around services, that is, in terms of how the traffic flows through the network, and do that in an automated fashion based on intelligence that we get from the network. And then this is all intent driven. I believe Jeff is going to talk about intent driven later on, so I won't go into that. And then on top of that, we've got some new service types that are coming in. So things like network slicing, you've probably heard of. There's a growing number of applications that require low latency or perhaps bounded latency. Other applications might require guaranteed bandwidth. And all of these things, I believe anyway, that the SRv6 network programming that I'm going to talk about today is really the enabling technology that allows us to do all of these things, to satisfy all of these requirements that I have on this slide. So in order to support network programming, we need an underlying technology, and that underlying technology is SRv6. And segment routing v6, I'm not sure if you're familiar with segment routing. I can give you the basics of it here. We don't have time to go into the real detail. But basically, it's a technology that allows us to define the entire journey that a particular packet is going to take. But the interesting thing about this is it's not just about the routers and the switches and so forth the packet's going to traverse, and that's really the segment routing piece, which is essentially a source routed path. But it's also about the processing that that packet must receive. So think about what services might want to be applied to that particular packet based on policy. Maybe there's some security that needs to be applied, or some accounting or OEM. That's what we mean by the processing on the packet. And also the reliability that the packet must have. So this is the failure protection. So the way this works is that the packet is going to get classified on ingress, and that ingress could be at different points in the network, typically in the access, but it could be even closer to the user, or it could be further away. But basically, once that classification has happened, the path that the packet's going to take is encoded as what we call a segment list in the packet header. And we use something called a segment routing header. And you can look at the details of that in RFC 8754. That's a piece of work that we finished a few months back. I think it was earlier this year. So the key innovation for SRv6 is this ability, I believe, to program the entire path. But it's both topological and processing instructions, and that's the key. And the second thing is that the state is in the packet, not in the network. Now, the network programming is going to build on top of SRv6, which is the underlying technology, and we'll talk about that next. So what is network programming? So when I talk to people about network programming, I typically get two questions, and that is this the same as SDN programming? Everybody's heard of SDN. Is that what we're talking about here? The simple answer is no. So SDN is really more about automation and mostly in the control plane. The other question I get is this some kind of new programming language? And again, the answer is no. So network programming kind of builds on top of SDN in the sense that what we're trying to do is turn the network into an innovation platform by introducing data plane programming. So in other words, what I'm going to be able to do is indicate in the packets themselves the processing that the packet's going to receive. And that kind of gets back to the previous slide where we talked about topological and different types of instructions that we can put into this packet. So the network programming essentially introduces a new paradigm in networking. So the key point to go away with is that this is packet routing with packet processing. So where the packet should go and how it should be processed. That's new. What we want to be able to do with this particular technology is use it to build the intelligent network-wide services that I talked about earlier. And the data plane we're going to use to get the packets to specific locations in the network, and then functions could be applied potentially or optionally with arguments along the path. So the data plane operation and concept here is that in SRv6 we have something called an SRv6 SID, a segment identifier, and this is 128 bits. Now this can be compressed, and I'll talk about that in a slide later on when we look at some of the things that we're going to be doing next from a development standpoint and standardization standpoint. And the network programming is basically coupled with IPv6 transport. And there's 3 levels of network programming capability. So what you see in this picture is the IPv6 header, and I've just got the destination and source addresses in there without all the other detail. And then following this is this thing that I mentioned earlier called a segment routing header. So the first level of programming capability is this flexible segment list. So what I can do is I can stack these segments in the list, and each instruction is going to get executed in a particular order. And by doing that, I'm able to program the network to do things like traffic engineer the packets, or maybe apply some service functions to the packets as well as traffic steer it, and various other things. The second thing is that there's flexibility in the segment itself, and this is the second level of programming. So we break this segment down into 3 things. The first thing is a locator. So this tells us, tells the network, bring this packet to this particular node. The next thing is a function which says execute this particular instruction. And then perhaps there's some arguments. So we tell the network to execute this particular instruction using these particular arguments. And then the third level of programming is the ability to carry optional TLVs. And this is where things like metadata might be carried that would give some context to different elements in the network to be able to do certain things to enforce the policy. So for example, perhaps I want to be able to carry identification of an application. And when a particular node looks at this TLV, it understands that this is this particular application, and therefore this particular policy applies, that kind of thing. So what's a function? What kind of instructions can I execute? Well, basically anything. Excuse me. So a couple of examples are, maybe the function identifies which particular layer 2 or layer 3 VPN this packet belongs to. Or maybe the function says apply a firewall, or apply some other kind of service function. Or maybe it tells you to execute a piece of code that you've actually written and deployed into the network yourself. So it's very flexible, and we're kind of really only starting to understand some of the use cases for the instructions that we might want to execute on these packets. But this gives you the capability to do these things. So the first level of network programming I like to think of as service chaining, which is an area that I've been involved in for a good 5 or 6 years. So it's kind of like the precursor, in my mind anyway, to the concept of SRv6 network programming. So what service chaining does is it allows you to kind of treat the network like an underground map. So if you look at this picture, if you remember in the previous slide, I've got a location, and I've got a function, and I've got arguments perhaps. So my location tells me the point of service application along a particular path. So for example, if I jump on the red line here, I'm going to visit a set of stations along the line, and they're always going to be those set of stations. But I can jump off at those stations and perhaps jump onto some other line based upon a policy. So maybe I jump off the red line at a particular station and jump onto the green line. So you can see it's kind of a flexible way of applying policy throughout the network, where I start off with a particular policy and I apply some services, but then the output of one of these services might tell me to go and execute some other service and kind of insert it into the middle. So you can think of things like perhaps there's some kind of suspicion that this particular packet flow, has something wrong with it. So maybe I want to go and take a better look at that. So I'm going to send it off down the green line where I'm going to do some scrubbing on that packet and take a look to see what's going on, that kind of thing. And then the function is the service to be applied. So that would be, each of these stations, maybe, I'm going to execute some kind of function. And then the argument is the metadata, as I spoke of before. So basically, this allowed me to create a dedicated and transport independent service plane. But it's not enough. So that's only really one application. And as I mentioned in the beginning, there's quite a few new requirements beyond just a service plane that are coming to us, primarily driven, as I said, from 5G. So we need more flexibility, in my opinion, in the data plane to address some of these requirements. So the network programming concept allows us to build that infrastructure consistent of the functions with the arguments that I mentioned before, and we can then apply those in a specific order at specific locations. And the requirements on the data plane, we've kind of covered this, but I just wanted to summarize them so it maybe becomes a little clearer. The data plane needs to be able to forward packets through a particular path to satisfy the location requirements. We need to be able to indicate how to process the packet, in other words, which function to apply. We need to be able to allow for reduction in network state, hence we want to use the segment routing. And we want to be able to provide the classification with policy enforcement at the edge and carry the result of that policy in the data plane through the selected path. Those are the requirements on our data plane. So let's look at a few examples then of this network program in action. So on this picture, what you can see is a router with what we call a local SID table. So it's got a set of segment identifiers, and these segment identifiers have got an instruction associated with them. So perhaps I receive a packet, comes in, and the SID is C::4. So I do a lookup in my local SID table, and this tells me that the instruction to apply to this packet is I want to capture a timestamp. So that's exactly what I do. I add the timestamp in a TLV in the SRH, which is the green block here, and I send the packet out of an interface, and away we go. Another packet comes in. It's got a different SID on it, C::3. So I do a lookup on this, and this tells me that I need to look at a TLV that is in the SRH, and I need to apply a segment routing policy based upon the received value. So in this particular case, I've got a TLV that comes in 1:1. So I go and look up the TLV, and this tells me to apply policy number 1, which is basically going to apply SR policy 1, send me out of interface 1 along my way, and using this particular segment list. Another packet comes in, it's got exactly the same SID, but a different TLV. And you can see that the instruction that I apply is the same, but the result is different because the value of the TLV is different. And in this case, I use segment routing policy number 2, which sends me down a different path. And then lastly, I've got a packet comes in with SID C::5. I do a lookup. In this case, it tells me to de-encapsulate the packet and do a lookup in a particular VRF. So I do my lookup in this particular VRF based on the destination address of the packet, and I send the packet out of interface 5 without any kind of segment routing on there. So what you can see is that this is very flexible. So there's lots of different things that you can do and different instructions that you can apply based upon which particular SID you receive in the packet and when you do the lookup. Now, of course, the interesting thing about all of this is, well, that's all great, but what can I actually do with this? So what I wanted to try and do was give you a few concrete suggestions that we're currently working on in the IETF, in the Spring Working Group. Some of this is kind of individual contribution work, and some of it is working group work that's actually been adopted and being worked on by the working group itself. So the first one, I think that gives you a flavor of some of the things that you might want to do is something that we're calling application or service aware networking. And this is kind of in its infancy in terms of standardization. We're working through that right now in the IETF. There's lots of IETF drafts that that I can point you to. But basically, this gives us an infrastructure where we want to be able to have edge devices that are application aware. So in other words, we want to be able to do some kind of application identification. And we want to be able to add that identification into the packet so that I can use it in the network to do some funky things. We want to have a head-in device, and this is something that's going to basically match to a segment routing policy according to the application requirements. So remember, at the edge, I've already identified the application. I've put that in the data packet, and some device upstream is going to look at the data packet and be able to take that information, map it to a segment routing policy, and do something with the packet. So here comes number one packet, and it's got, this is the destination to this router. This is the SID, and it's carrying a TLV. Now this TLV just happens to be the gold service, which is segment routing policy number one. So I do a lookup in my SID table, I do a lookup on the TLV, and I send the packet down the gold path, which is this path going through the network. Another packet comes in, same SID, but a different TLV. This gets silver treatment. In other words, it gets a different policy applied, and it gets sent down the silver path through the network. And then lastly, I've got another one comes in. This is the bronze service. As you can see, that gets a different segment routing policy, and therefore it goes down the bronze path in the network. So depending on which application it is, depending on how important that application is, I can assign it to maybe my gold or my silver or my bronze service, which for the most important applications or applications that require maybe low latency, will go down, let's say, the gold path, whereas other applications would go down the other different paths. So this is a piece of work that we're working on right now in the IETF. I put some of the stuff here. Basically, the idea is that we've got application-aware identification. So this information could be an SLA level, which is the one I just described. It could be an application ID, could be a user identification, it could be a flow identification. There's also network performance requirements. So that information perhaps is the bandwidth requirement of the application, or maybe the latency requirement. Maybe there's some packet loss ratio or some jitter requirement. So all of these things are information that we can carry in the data plane to apply a particular policy. There's some IETF drafts you can go, here's a couple here you can go and look at, which is a problem statement and kind of like a framework, if you will, that looks at in more detail some of the things that I just described. And some of the services that we're looking at that would utilize this kind of thing are things like ApplicationAware SRv6 for SD-WAN. There's integration of SRv6 for DetNet. So DetNet is another technology that's been worked on in the IETF, which is specifically to do with low latency applications. We might want to do path selection or fine granular traffic operations. There's also network slicing, which I'll talk about in a couple of slides. There's network telemetry, something called IFIT, which we've been working on for a while, which is a framework that covers lots of areas in the telemetry world. Maybe application-aware SFC. So perhaps what I want to be able to do is identify the application, and depending upon which application it is, will allow me to put a much simpler policy in my firewall that matches on application rather than source destination address. Those types of things. The second thing is we started to integrate some of the service chaining work that we did in the SFC working group. In this working group, we created a protocol called Network Service Header, which was basically, I mentioned it earlier, it gives us a transport independent way of doing service chaining. But what we've also been doing is integrating that with SRv6 service chaining so that we have the ability to do just SRv6 type service chaining, or just NSH service chaining, or a combination of the two. And there's lots of work going on here. I've put some pointers to some of the RFCs and drafts that are important from this perspective. But there's also some new work that we've been doing. I started a document looking at ways to utilize the TLV capability in the SRH to provide metadata support to firewalls. So there's a document you can go and read there. There's a control plane framework that we've been working on as well. Another big area is network slicing. So this is a concept that we want to be able to segment, if you like, our network and have specific resources available to different slices. So for example, I might want to reserve some resources at different points in the network that are dedicated to a particular slice. And we can use SRv6 to support this network slicing concept by allocating or dedicating some locators for each of the network slices. And the SIDs basically inherit the slice information of the locator. So what we can do with this is use those SIDs to identify the network resources that are being allocated to that slice and be able to apply relevant resources to the packet flows that belong to these independent slices in the network. There's some documents here that I've pointed to. One is a working group document in the Spring Working Group, which is talking about resource-aware segments. So this is, like I describe here, you've got segments that are dedicated to particular resources on a particular device. And by doing a lookup on this resource, the instruction will be applied based upon those resources. And then there's a document that talks about how you might use network slicing or segment routing based network slicing in a network to support this kind of environment. Another area is seamless redundancy. So this is utilizing the DetNet concept that I mentioned before. So what we want to be able to do is use SRv6 to steer the packets with a particular segment list in the SRH, and be able to indicate the packet processing, including things like replication and elimination and ordering, which are things that are specific to the DetNet technology. So we can do this by extending some of the SID functions. We can carry flow identification and sequence numbering in some TLVs in the SRH. And there's a document here that talks about all of this if you want more detail. And this is kind of a picture that shows, I've got this packet going along. I'm going to replicate it because I don't want to lose traffic. And then I'm going to eliminate one of those particular replications at some device in the network and then deliver the packet along its way down the path. Okay, so what next? So there's lots of work going on in the Spring Working Group. It's probably one of the most active working groups in the routing area in the IETF. I think if you go and look, I forget how many individual documents there are now. Last time I counted, there was close to 100, I think. But lots of different things going on in lots of different areas. One big area that we've been looking at is compression design. So one of the things that we've wanted to be able to do for some time, and we've recognized as being probably necessary in the future, but based on deployments now, I would say this isn't really necessary. But we think it will be in the future. And the reason for this is that in SRv6, the SIDs are 128 bits. So this is fine if you've got, a handful of SIDs on the packet, but there are certain use cases that that we've identified that, perhaps you might need like 10 of these things. And then the overhead on the packet starts to get unwieldy. So we've been looking at ways to compress the SIDs. So for example, maybe what we want to do is compress them down to 32 bits. And there's lots of different ways to do this. And we've got a design team in the SFC, Spring Working Group that's actually working on this particular thing right now. This kind of slide just shows you that what we want to be able to do is utilize the segment routing header, but make it very flexible, so that it's backwards compatible in terms of, we can still carry 128-bit SIDs if we want to, but we also want to be able to carry smaller SIDs, like maybe 32 bits, and we need a way to do that. Now, as I said, there's several solutions that are on the table for this. One of the ones that I've been involved in is something called generalized SRv6. So this is something that that we're working on. As I say, this is an individual kind of contribution at this point, and the design team that we've got going in the Spring Working Group is kind of reviewing all of the different options. So this is one option. And basically what we do here is we use something called a compressible SID. And a compressible SID, the concept is actually very straightforward. So one of the things that I noticed when I looked at the deployments was that the IPv6 address space that the SIDs were allocated from had a common prefix. And in a lot of cases, those prefixes were at least 64 bits, if not longer. So you can imagine that, well, if every SID has this common prefix, then why do I need to carry it in the packet at all? I already know what it is by looking at the first IPv6 address that I receive for this particular traffic flow. And all subsequent entries in the segment list only need to carry the information that's unique. So using that kind of mechanism, I can drastically reduce the size of the SID. Now, we want to go potentially one step further and make the SRH actually flexible, in the sense that I can carry SIDs that are 128 bits. I can carry SIDs that are 32 bits in length as well. And there's lots of different reasons why I might want to do that in terms of the use cases that we've seen. This is a piece of work that we've been looking at to actually extend the SRH to make it more generalized in support of some of the requirements that we have. And there's some documents down there that you can go away and read. Now, I know I'm running out of time, so in summary, basically, I think that SRv6, and more specifically the network programming concept, is really the next logical step for IP networking. And I believe that it's the only technology that can really unify the network end to end. It gives us the infrastructure to enable an intelligent IP network. So this is the source routing capability combined with the network programming capability. As I mentioned, the key benefits are the network simplification and the network programming. The message I would give to you is that the standardization is pretty mature at this point. As I mentioned earlier, the SRH is already an RFC, and the network programming document is with the IESG in its final stages as we speak. And if you're not familiar with the whole process of IETF, when it goes to the IESG, we're actually requesting them to publish it as an RFC. So what happens in this case is experts from all the different areas in the IETF will take a look at the document to make sure it's accurate from a technical perspective, but also that it doesn't affect other areas. You know, I'm a routing guy that knows absolutely nothing about network management, so maybe I'm going to screw something up. So I'm going to have a network management expert look this document over, and you know, by this mechanism, we get a much more robust document. And in conclusion, we're really, the company that I personally work for is really driving a lot of the innovation of SRv6, such as the network slicing and the service chaining, the application-aware networking, a lot of the compression work, and I mentioned the GSRH as well. So, so I'm going to, do I have time for questions,
Yes.
Drove, or no?
We have, we'll have to do it very, very quickly.
Yep.
Jim, we have one question on SRv6 Plus, which is basically CRH. And just to be fair, it would be also good to just compare and contrast the GSRv6 with CRH. Just a very quick, we can give folks know that there are other compression solutions out there as well.
Yeah, so SRv6 Plus, or CRH, basically, it's another. It's essentially the same in the sense that it uses a routing header, and in simplified terms, the key difference is that they use IPv6 extension headers as opposed to the approach that we've taken with the TLVs and so forth, to essentially do the same things as SRv6. The downside is that in order to support that kind of thing, you introduce state into the network and you need a mapping system. I would prefer personally to carry all the information I need in the packet. I don't want to have a mapping system in the network. Other people may want that. So, you know, you need to compare and contrast the two. They're both trying to achieve the same things. And that's really all that we can say about that at this point in time, I would say.
Thanks, Jim. Jim, one question from Joe, which is related to any work to increase the underlying MTU to simplify packet header processing. Not sure. Exactly
not aware
what,
of any.
Yeah.
I'm not aware of any. I mean, obviously, one of the issues, you know, obviously, is that we need to make sure that that the packets that flow don't, you know, break that MTU. So one of the reasons for doing the compression is to reduce the size of the overhead, and then, you know, hopefully we don't get into that situation. But I'm not aware of any specific work that's going on in that area.
Okay.
I think,
Jim, can I request you to? There are two questions, but those can be easily answered by text. So maybe you can answer them by typing. And
I can see them. Yeah, I can see them both now, and I can actually answer them pretty quick. Open source code, yes, I know there's code in VPP, which is the Cisco VPP code. The inter-AS and inter-domain, that's kind of an area that is still being looked at. There is some work in that area. I'll try and answer that one and point you to some documents on that. But yes, it's an area actually that I did a lot of work on in the MPLS days with the VPN. So I'm pretty familiar with the issues there. So yes, there is some work going on, but it's, I would say, early days.
Jim, I believe free range routing is implementing a SRv6 VPN to be in stock enough.
Okay. Okay, I think that's it. I'm happy if anybody has any burning questions. My email is on the front page of those slides. Feel free to email me. I will certainly respond as best as I can. And I hope it was useful.
Yeah, thank you. It was really useful. Thank you. Okay, let's move on. We are running a little late, so let's move on to the next presentation, which is MADINAS. This was MAC address device identification for network and application, a BOF that was recently discussed at IETF 109, and we asked Michael to come and update the group on what happened there. Michael is an open source and open standard consultant. He has been involved in networking for a long time, from designing and building embedded network products, mainly in security side. He has operated many networks, worked on DNSSEC, root name server, built boutique ISP. Really, we are really grateful for Michael to be back at Connections. He has been working on the IoT mesh routing, basically the role working group. And we are really happy to Mike to come and talk to us about what happened at IETF 109. So after you, Mike, I'll stop sharing and you can share your screen.
Hi. Is that working?
Yes.
Wonderful. Okay, so I did put the slides at this URL, and if you're really fast with your phone, you can probably capture that out of that QR code for there. My screen shows a nice picture of green and orange. Are my slides still being displayed? Yeah, okay. Who am I? Yeah, Drew introduced me. That's great. Some logos and stuff I've been involved in over the years, and mostly I've worked in a number of startup companies, and between that as consultants, and figured out that was the right way to go. So we're going to talk about what has happened to this, and I threw some links here. Probably the easiest way to find out what happened on your own is to go and watch this YouTube link here. That has the complete recording. IETF sessions are all pretty much recorded, and for extra fun, you can play it back at either super fast or super slow, depending on what you like. And this BOF has this URL. So this is what was called a non-working group forming BOF, which basically means a bird of feathers session to discuss the question about essentially if there's a problem, and if there's a problem, what would the IETF do, without getting to the details of what we're actually going to do. So there's a lot of slides there and some interesting stuff that happened. And I'm just going to walk through the overview of what they talked about and why they're talking about it. And then we're going to talk about what are some of the effects we do nothing, or what's worrying people here. So this is a picture I got off of a really pretty website on that explained Wi-Fi packets. It was a really nice, pretty packet. I really liked it. And if you're familiar with Ethernet, you may go, wait, hang on here, wait a minute. This has got 3 MAC addresses. That's right. You can have Wi-Fi packets have 2, 3, even 4 MAC addresses. And there's some other stuff in there as well. So this part in the purple, this frame body, that will typically get encrypted if you have enabled encryption in your Wi-Fi, which most of you probably have. In most cases, you've done that. But the source address, MAC address, here in this pink or fuchsia color, it's always in the clear. Okay, so that's something to realize. Regardless of how much encryption you apply, that's always in the clear. In fact, in some modes of encryption for Wi-Fi, that station address goes into how the packet is encrypted to make different packets look differently. That's particularly the case with 802.15.4, which is a different wireless standard. So the issue is that because it's always in the clear, it can always be seen. And so the issue was essentially as you walk by some nice network, and the network announces itself to you, and you say to them, hey, network, how you doing? My identity is, and that's your identity because it's the only thing you have at this point, your MAC address. I shortened it a little bit for editorial reasons. Of course, there's 6 or 8 bytes in that. Can I go join your network? And the network says, hey, maybe, but since you told me who you are, that's really great. I'm nice to see you again, George. Okay. And so that's what people have been worried about. And they've been worried about this for at least 10 years now about what's going on. And so people have done some things. It's not really new. So what happens today, typically with most phones, is that MAC address is chosen randomly. Each time you encounter a new network, you pick a new random address, and then you keep that address for, well, up to now until ever. So that means that if you return to the foo network knows you're back and can apply whatever access control lists or tracking it might have done to you again. So, Starbucks is always the canonical coffee shop example. And I found this nice map of Starbucks locations. And it's interesting, that that's a US map of the US, and the density of those green dots is pretty impressive, I think. So any one of those, of course, have probably the network called Starbucks, and they can all track you. And of course, if Drew puts up his network and calls it Starbucks, and sells you only pour water, he can also track you. So this is what's been the problem here, right? So things have changed a little bit, and the IEEE has done some things. And it turns out that, for instance, if you had an iPhone and it randomized the MAC address, and someone else, your friends, has an Android phone which has a randomized MAC address, turns out that observers could, for instance, learn whether you had an Android or an Apple because they randomized the MAC addresses sufficiently different that you could tell the difference. So the IEEE now has an official process for randomizing the MAC addresses, and things have gone on a little bit. So what's changed? So now, as of iOS 14, and there's some differences between the beta and the release, and I don't know what those are, but as of that point, it will in fact not only randomize the MAC address each time it does, but it says in the second box, every now and then it will change it and put up a new address there. Android hasn't decided yet to do that, and I think it will probably be a little bit of a pause. This is a box about what is currently the state of the art on Windows, okay? So typically, use permanent hardware MAC address. That's one of the options. Use the same random MAC address every time. So that's what Android does and what iPhone did until recently. Or change daily. Use a new random MAC address every day. So that means we throw away the new address you had today, at the beginning of the tomorrow, and we make up a new one. So that's what I just said. So what are the effects? Well, you think, okay, well, what does this really matter to me? I mean, what's going on? Well, in your home, you have a WPA with a password, with a Wi-Fi password, and no other access control lists, so just a stock kind of system. Then after the interval, the device changes its address. That causes them to lose his Wi-Fi association, so he reauthenticates and gets back on the network. And that probably happens with you even noticing, and probably happens in the time the phone or something awakens again through that wake process. On your router, the IPv4 ARP and IPv6 neighbor caches get updated with your new address and new MAC address. And unless you do something specific, you probably are going to get a new IPv4 address. So that's kind of interesting, because that could break some of your TCP connections that you might have had alive. Or perhaps you're going to use the same DHCP has a thing called a DUID, and maybe if you use the same one, you'll get the same address back. I don't know what will happen about this, but that's part of the point of the conversation at the IETF, is to figure out what's going to happen. If you're on an enterprise with certificates, mostly the same situation, but enterprises typically have a lot more users per MAC per size of their V4 address pool. So in your home network, you probably have 254 IPv4 addresses available. That's probably have maybe only 130 or something, depending on configuration. But that's probably more than enough for you and your spouse and your 3 kids and your cat's tracking device to change their address once a day, even if the lease is maybe a couple hours. So the issue is that the router gave up the lease for a period of time, maybe a couple hours to a couple days, maybe as long as 7 days. And if it runs out of addresses in its pool, then nobody can work. And an enterprise, which may have a lot more users coming and going and a lot more things, the pool could get exhausted. And that's a concern, because it looks like the network breaks when in fact there isn't really a problem. Well, what if you have some access control lists? Okay, so like an accept list, or what we used to call a white list. So maybe, you've said that the kid's not allowed to use their phone after 9 p.m. I have that argument every night. And I consider putting this control in. So I would put the kid's MAC address on some list that says from 9 a.m., I don't know, from 7 a.m. to 9 p.m. it's allowed to use the internet, and the rest of the time he's not. Well, then he changes his MAC address. Oops, my access control list is broken. It doesn't do the right thing anymore. So I'm sure you've all been to hotels and hotspots and other places with what's called a captive portal. So you have to log into something, and you have to say, agree to their terms and conditions, and maybe you even have to pay. And now your phone changes its address, and what happens? You have to pay again. Okay, that's not good. That's a real fail, and that's why, in fact, when Apple first started randomizing MAC addresses, they stopped doing it. They put that rule, and we keep the same one for the same location. So when you do visit the Starbucks, etc., you usually don't stay there for 12 or 40, 24 hours. At least I don't. They kick me out. And so you probably never notice if it changed from day to day, and it wouldn't be a problem. And this would, in fact, would stop them from being able to track you. So you get there and you authenticate, and that's great. Okay. You go through the click through and you're all good. So what's going on? This conversation at this BOF was essentially a number of people who presented the situations where they were. You can read those presentations or go through the video. And a bunch of variety of users. Some of them are enterprises users who have access control lists, who often register their devices by the MAC address of the device, and they create a list who's allowed, who's an employee and must be on the employee network and must be maybe filtered by the enterprise's forced proxy, And who's a guest who brought their own device and therefore gets a different level of access. Maybe can't talk to printers, but isn't filters as strong. There's all sorts of different things to do this. As I mentioned, the home users, the teenager child devices, restrictions against people accessing adult content from certain devices. And so those people who sell these things are concerned because suddenly their mechanism of identifying users is a problem. You might not know that ISPs that provide their own home routers to the users, which is the vast majority of ISPs do this, and users accept whatever they're given because they don't know any better. They usually have some kind of a system to manage the home network. TR69 from the Broadband Forum is commonly used, and it usually provides the ISP with a view into all of the devices which are in use in the home. This is not necessarily for nefarious uses of spying or stuff. It's usually to help the home user figure out why their network is toasted. Okay, and so the MAC addresses provide them with key handles in which to control things, so they can reduce the amount of bandwidth used by the kid's phone that's streaming or playing games all the time, so that parents can do a Zoom meeting, for instance, or that, or a bunch of other things. And usually what happens is the user calls up, the homeowner calls up the ISP, and the ISP has this view. Now suddenly they're going to lose this view because the MAC addresses keep changing, so the stuff all breaks. So a lot of their value add that they have is now gone. Okay. And then there's some other vendors who, for some reason, seem to think that it's reasonable to try to deal with malware by putting the misbehaving devices on a deny list. So that never really worked, because a really bad device could just change its MAC address and could do something. A truly infected desktop could do that anytime it wanted to. The right answer, of course, is the opposite. You have to make an accept list, and you have to treat everything else as suspicious. So I have very little sympathy for these vendors. They did it wrong from the beginning, but now they're really up a creek. So what are the opportunities? Well, all these guys are going to have to rethink how they're doing. That means pretty much every single ISP on the planet and every single vendor of enhanced home networking stuff. So they're going to have to deploy new codes. So I would say it's time to provide for strong authorization for devices based on identities not trivially revealed or trivially changed. So this renders right into IoT devices, for instance, that need to be identified by their IDEV ID, and they need to be enrolled. And this is not happening today, and we have a serious problem with that. Okay. Last week I did a series of tutorials on changing default passwords, and I just stole this slide out, and I thought I'd keep it. I love the orange. This is a list of onboarding solutions that are out there. We have a plethora of them. Plus, I think not on the slide is the FIDO Alliance has an IoT mechanism as well. There's a lot of different mechanisms. All of these are aimed at constrained devices. There's no reason they can't do it for phones or desktop PCs. And some of them just would work just out of the box with that too. If you do want to listen to that, the URL has the videos and the slides for that. But essentially the process is that you do some kind of interaction with the device. Here I have the friendly teddy bear webcam, which apparently has some 100 vulnerabilities out there. You scan it with your phone. There's some crypto involved, and you get a relationship with the thing, and then you do something. And there's a long list of different ways we could do that. So what does it mean here? If you do this, it means that each one of your devices would have an identity, and they would authenticate. They would start using WP Enterprise instead of WP PSK. But that's not such a big deal. It's pretty much all the codes all out there. Almost all the phones and desktops already support that. And pretty much all the code in most of the OpenWRT, at least based home routers, already has all that code in there as well. People think, oh, I need to have a radius server and a whole bunch of stuff like that. And yeah, you could build it that way, or you could just simplify your life and not do it that way. It's not required by the protocols. So we have here a bunch of ducks here with different colors, and they get, different policies. The yellow duck is always allowed. The purple duck is allowed from 9 to 5. The green duck is allowed just till tomorrow at 11:30 when they check out of the hotel. And the dark purple duck is not allowed at all. It's considered unscrupulous. What happens? You translate that policy, guess what, into a MAC address, and you implement it in hardware. And when the device changes its MAC address, well, it has to re-authenticate. At which point you learn its new MAC address and you do it again. At no point do you have to reveal the identity to anyone watching, because that all happens essentially. WP Enterprise is a TLS connection over the network. So conclusions: MAC addresses were always terrible identities. They were shortcuts, and they resulted in a little bit of short-term gain, but long-term pain. And onboarding provides identities. So we have lots of choices. We just need to use it. And that's it. I think that's my last slide. Oh, I put up some resources for that, and I have a bunch more if you want in these slides. Any questions? I can find out the question, the Q&A box. There we go. Someone says the same thing with MAC addresses with Bluetooth. I'm not sure if that's a question, Joe. So if you want to add something or speak up, I'm not sure how I would answer your question. Yes, it's true. MAC addresses are also in Bluetooth, but Bluetooth has significantly less range. So while I can walk into the hotel lobby with my Bluetooth antenna and probably capture a lot of stuff, mostly I need to walk up within a couple feet of you. And if I'm standing in a couple feet of you in your hotel room, you probably would notice. Also, if you show my house that way.
Yeah, so the Bluetooth community just added random MAC addresses.
Okay.
Which is making it very hard when you're dealing with maintaining a connection, especially when you're doing frequency hopping. So it's actually pretty funny to watch them go through this process.
Well, but isn't the accept list for Bluetooth anyway based upon the pairings based upon MAC address?
Yes, in some cases they're trying to do it with authentication, but the authentication is either 64-bit or 128-bit. It's relatively weak.
Huh. Okay. Thanks for that.
So yeah, lots of different organizations are trying to do exactly the same thing.
So Balaji S says, are certificates the only known stable solution till now to identify the device uniquely? Well, you could make up something else. You need something asymmetric. So that means that you don't have to, you can safely reveal the public part to the network infrastructure in such a way that it can't impersonate you. Whereas a symmetric key allows anyone who has it to impersonate you. So that's not really a good choice. Certificates could be self-signed. They could be essentially there. We can use raw public keys. TLS supports that. The problem with raw public keys is mostly that people don't know how to use them and they don't know how to exchange them. And there's a lot of people that don't understand them. And so somehow a self-signed certificate is acceptable, but a raw public key is not. I'm a great advocate for more use of raw public keys, and that would be this would be a useful place for doing this, since it really doesn't matter who signed your thing or what it is when you're joining a thing. What matters is that you're the same person you were last time. So no, you don't need a certificate, but you do need something asymmetric for that. In the IoT space, where the devices are need to be able to onboard without necessarily complicated access, a screen, a keyboard, and an operator knows what they're doing, then having a manufacturer signed IDEV ID has a significant advantage, because it allows the network to identify what the device is and what kind of device it is. And if you've been to any of the connections in the last 2 or 3 years, you've also heard about MUD files and from Elliot Lear and myself, and being able to reference the MUD file and certificate is a pretty important step for an IoT device. Anyone else? Is there a chat? Where's the chat?
Yeah, Michael, I've got one. This is Nalini.
Hi.
Yeah, hi. Thanks for doing this. This is really great. I tell you something. I use MAC addresses all the time when I'm diagnosing problems. I use their to address. And because I tell you, I was just looking at something the other day, and it was hard to tell if the trace had been, because we had a duplicate packet and I was trying to figure out, was it taken on you know, like, well, actually this one happened to be at the end device or the Cisco, you know what I mean? But
Right.
anyway, cut a long story short, I could figure out from looking at the MAC address. So I suppose the thing is like, I totally get that this reveals a bunch of information, but I tell you, it's super helpful.
Yeah, so it's clear, to be clear, we're not talking about changing the MAC addresses on a minute-by-minute basis, right? We're talking about in certain, depending on the settings that different people do, and I think that the IETF is, well, I don't know if the IETF is going to form a working group. There's an IEEE effort as well, but I think that those three settings that the Microsoft thing had, which was essentially off, you know, just use the same MAC address, don't randomize at all. On, use a random MAC address, but it's the same address each time, which is almost the same effect, especially for a system that doesn't move anywhere, like your refrigerator or something, or your printer, okay, desktop PC at work, or change daily. Well, I think that makes no sense for any device that's not mobile. That's just asking for diagnostic hassle. So I think in an enterprise setting, I think it's going to be pretty much either permanent hardware MAC address or the same random MAC address all the time. And I think that Android will adopt those three options. And I think that Apple will be persuaded to provide that setting more clearly. From what I can understand, it's maybe there in some places. The problem is really, as you said, is if you had that packet trace during the time that the address changed, that could be really confusing. I don't know what's going to happen with the IPv4 assignments with DHCP. I guess we're going to see, and I think there'll be some tweaks and some changes, and there'll be some people's noses bent out of shape when they realize that, you know, having their friend over with that particular device exhausted their network pool and broke their network. So we'll see shorter DHCP lease times, like down to 2 hours. It would sound reasonable, even in the home. So I don't know. I don't know if the IETF will have a working group, but I don't know what we would say, but I think we'll do something.
Yeah. Thanks, Michael.
Thanks, Mike. Mike, can I ask one question to you? Because we have asked some people who want to bring in some new work to IETF, and as we know, BOF is the way to achieve that. So this question could be to you as well as for Jeff, because Jeff is on IAB, and IAB helps to shepherd new work into IETF. So do you have a few words that you would like to say on people who have new ideas and who would like to bring in work to IETF? What are the must do and things to look out for before they do that? So maybe this question is for both you and
So
Jeff.
I think this is a good BOF. If you're interested in bringing new work to the IETF, I think this is worth an hour. Going and watching this BOF for an hour and you can probably make that half an hour with 2x speed if you want. It's worthwhile doing. I think it's important. The important things about this BOF is that nobody really talked about solutions, and I talked for longer about solutions to you guys than I think I said one or two things at the microphone in that BOF. But I knew it was not a time to talk about the solutions. The problem it's to establish what the problem is. That's really the primary thing in it when you bring new work in. Don't start with your solution. Start with your problem. Okay. If we'd had time, I would have asked this previous speaker, what does SRv4 do that DiffServ 20 years ago didn't do? I don't know what the problem that in the end that he's really trying to solve is. Although I know a fair bit about SRv6, I still don't quite know why it is that we couldn't do it with existing tools. Why did they fail? And I think that's an important question to ask. What is it about things that are out there that are broken and couldn't do? You will get questions when you do bring work. You will get questions. Why is it different than this other thing? And you may discover that there are things that have been tried in the past and they seem identical to yours and have failed in the past, or people think have failed in the past, Or in some cases, I was a part of a company 20 years ago that we did some stuff. We learned that Cisco had tried it 8 years ago and it failed. And so everyone at Cisco that we talked to about our stuff said, "Oh, we did that. It's stupid." And we said, "Yeah, but this is 8 years later of technology. RAM's so much bigger." And some of them went, "Huh, yeah, you're right. We could only buy 16 kilobit, SRAMs at the time, and now you can buy multi-megabit SRAMs. Actually, it might have succeeded if we tried now." And so you actually have to realize, if it's been tried before, what's different? There's something different maybe now that's different than before, and you may actually have to do a fair bit of research into why things failed before or why people hated them before. So Shashank Jain asks, how is the adoption of client certificates among IoT devices? Any IoT devices already using certificates? Yes, many. Sadly, I'm going to tell you that the number of NDAs around this is larger than the number of devices deployed, it seems. Basically, anything that you see that's being deployed from through an Amazon link up or an Intel SDO link up or Device Authority or Rambus or ESP Global, there's a whole list of these places that are actively doing some kind of IDEV-ID identity. Sometimes these are symmetric keys that are put in place and are later turned into an identity during a provisioning process. So you won't see it listed as a certificate rather as a secure seed or something else like this. And it seems to be going on a lot, and a lot more than people thought as well. But the problem is, what are you going to do with a certificate in the home? You're not seeing it in consumer devices, but the cloud sees them. So I think that there's Amazon Echoes. I think that they talk to Amazon with a certificate, not to each other. Yeah, so Joe Klein says, problem is IEEE is seeing is very cheap IO devices all sharing the same MAC address. Yeah, and I wish actually, Joe, that we could make that an import regulation and just kick them out at the border. I actually bought 50 USB Ethernet devices for use in a project, and they didn't have the same MAC address, but they did go 1, 2, 3, 4, 5, 6, with the rest being zeros. It took me a while to notice it actually. And I went, oh, that's weird. A lot of zeros in that MAC address. And that's because they just hadn't bothered to pay IEEE the $2,500. So when we get to randomized MAC addresses, the question actually I think the IEEE has to ask is, why would I ever buy an OEUI from the IEEE if I'm always going to put a randomized MAC address in? That seems way simpler to me.
Thanks, Michael.
Okay, well, I'm going to go to sleep now. Good luck, Jeff.
Thank you.
Jeff, while I bring up this thing, do you want to say a few words on the BOF part as well? Because you have quite a bit of experience in getting new work in IETF. So any feedback for folks in India and otherwise who want to bring new work to IETF?
Yeah, absolutely. So BOFs being discussed between ISG and IB significant amount of time before IETF. So there are a number of criteria. Some of them are decent amount of people who support and willing to work on it. You are not boiling the ocean. Technology is valid, not necessarily very well understood because it's just a starting point. But I mean, we are people with a lot of experience in networking and standardization. So at least on God's feeling, there should be consensus about value of this work. And it requires a lot of work from supporters and organizers to get this stuff done. There've been a lot of reasonably interesting proposals and technologies where organizer would just, give up, not put enough effort, enough time, and people would just, if you're the main proposal and you're not interested in it, why should we? So it's really perseverance and your soft skills, ability to influence people, ability to explain to people why technology you're proposing is good, important, and how it would benefit the community. Right, so you see it's a combination of being good technologists, being good, I mean, politically it's not a good word, but being good with people, being able to work with people, because that's what IETF is about. You could be a genius, but if you cannot work with other people, you will never succeed.
Thanks, Jeff. So we went a little out of order. Let me now introduce Jeff and the next topic, which is intent-based networking. And Jeff has 25 years of experience, has written many RFCs and patents. He has been involved in IETF and running the RTGWG working group, as well as the RIFT working group. He has been involved in bringing in a lot of new work to IETF. He's currently serving on the IAB and focusing on the 5G and network slicing work. He's also involved in the ISOC chapter at the SF Bay Area. Currently, he's the head of networking strategy at Apstra, and the company that has been focusing on the intent-based networking. So it's really great to have Jeff as part of Connections and talk to him about intent. Off to you, Jeff.
Thank you, Drew. Let me share my screen and we'll start. You should be able to see my screen, right?
Yes.
So hi, everyone. Thank you for being here. Thank you for connecting with us. It's important to understand what's going on in the industry, and it's my pleasure with my colleagues, Jim and Andrew, to share with you what we see, what we are working on, and what's happening. So why intent-based networking? Since foundation of networking in 60s, network automation, network management has been an afterthought. We would build network, we would build devices, we would build features, and then start thinking how to manage them, how to operate them. So it has always been an afterthought and really second-class citizen. Given the complexity of today's networking, given the number of devices and complexity of technologies on top of them, we as humans, we cannot comprehend this complexity. So someone has to happen. And this is where intent-based networking is coming in. And, you know, we've tried many times. If you look at the industry, if you look at last 20 years, we've tried many times to make networks being more operator-friendly. However, in a lot of cases, people were too busy to build more and more complexity. So it's a funny picture, but as sad as it sounds, it's the truth. It's just about now 5 to 7 years ago, IETF started working on young industry, started to really think about networking as distributed system. And I mean, it's not distributed systems is not a new science. It's been around for many years, but we've never treated network in such a way. In order to understand what to do with network, you need to think about network as a whole entity that includes distributed elements and runs protocols between them. But the outcome of the technology, the outcome of your intent is fully working network. It's not one part of it or one device. So IBN is a holistic technology that looks at outcomes, and we will go in much more details. So if we look at today's IBN landscape, we see what we call IBN washing. So there are many companies claiming we are IBN. Choose your favorite company, they'll probably say this. However, if you, as technologists, incapable to provide full life cycle from design to operations, you will see only part of the feature. So in this case, you see some people see a wall, some people see a rope, a tree, while this is an elephant. So point being, unless you treat network as a whole, as a distributed system, you will see only part of it, and the end result is going to be incorrect. With regards to landscape today, so if you go completely into extreme lock-in single vendor, probably you'll get some software on top of your gear to automate it, to manage it. So just pick up your vendor. On another side, you want to go into multi-vendor, you're okay with scripting, you know Python, you could probably use Ansible books or similar tools. And it's perfectly fine for level 0, what we call basic automation. So you have a repetitive task, you need to configure VLAN on 100 devices, perfectly fine to use a script. However, none of these tools can really deal with changes in the network. This is where introduction of level 1, the single source of truth, is becoming so important. And if you look at modern NOSes, modern systems that's being built now, they all have this single source of truth, and the rest is ephemeral. So you don't treat configuration and treat it as source of truth. You've got something like Redis or similar database that holds the intended state. So I would really like to focus for this presentation on real-time change validation. This is really complex piece because changes are happening all the time. You deploy a new network, 2 minutes after that, it's not a green field anymore. Something has changed. So how to look at the change holistically, how to understand what the change is impacting. This is really, really complex piece of technology, and probably last barrier that doesn't allow us to get to networks that can self-operate, which is really the nirvana of networking. So standardization part, there's really great progress. We've written a draft that defines what IBN is. And it outlines numbers of really, really important building blocks that any IBN system should have. So single source of truth, you're going to see the team of SSOT going through whole presentation. Intent-based analytics that are not put as an afterthought after you have deployed your network, but part of your intent consumption. So during design phase, when you express and model your network, you already know what to expect from it. This is how IBA is being deployed in well-designed IBNs. PDP and PEP, in order to apply policies in vendor, hardware, technology agnostic way, you need to model in such a way. So this is where we define policy decision point. Really, endpoint A cannot talk to endpoint B. And then policy enforcement point, which is vendor, hardware, software dependent, will enforce this in particular way. So if it's a switch or router, it could be an ACL. If it's a firewall, it could be a rule. If it's a public cloud, again, could be similar concept, NACL, ACL on public cloud. So by decoupling decision from enforcement, we make policy definition, hardware and technology agnostic. Back to the draft, it's on its way to become RFC. We are going through research group last call. It's very stable, so with small changes, I think we are ready. Very, very good document, very readable. I would highly advise to reading it to better understand what intent-based networking is really. So why data center is such a great point to start with IBN. And this is where company I'm working for, Apstra, started. Today's data center, I mean, most of them, 95% of them are using leaf spine topologies or CLO, after name of French researcher who defined this topology. The beautiful part of the kind of topologies, they're very regular and uniform, and they expand in very predictable way. From very small network with a bunch of leaf and spine to 5-stage network with additional layer to huge 16-pack alike scenario in Facebook, they all follow same rules. Leaves are connected to spines, spines are connected to super spine. There should be never link in between. So you might see something like multi-chassis lock and some other artifacts of today's networking, but they're really breaking it. They're not making it better. So in properly designed and done CLO network, you would see this repetitive pattern where lower layer connects into higher level. And in order to get to another part of it, so from leaf 1 in pod 1 to leaf 4, you have to go through spine. If you want to get from pod 1 into pod 2, you go through superspine. So in such network that is very, very predictable, it's easy to define outcomes. And intent-based network is all about outcomes. So if we're looking at Telco 1 today, the story is very different. There's very little greenfield, which is quite different from data centers. And while we designed beautiful network for day 0, 2 years later, it looks really like picture on the right? No one knows why it looks this way. You see thousands of tunnels, no one else does the configuration. So the issue is much more serious and will require much, much more work. And I don't think there's really a way to avoid it, because complexity is growing, number of devices is growing, requirements are changing from being mostly best effort to network slicing derived when you need to provide services with very low latency and virtually no packet loss and such thing. So there's a hope. In IETF TS working group, and this is work where Dhruv is very involved and driving a lot of technology, we've identified and defined framework called ACTN that defines number of layers and interfaces between them. So network user layer, carrier layer, and vendor layer. It's all driven by young work that we do in IETF and other bodies, and gives us ability to provide correct layers of abstraction and build multi-layer networking that could use intent-based networking on top of it to instantiate services. To add to that, so traditional multi-layer networking has been very complex for years. You know that optimization for more than one train is NP complete. So doing this kind of computation is very, very intensive and very difficult. With 5G, the complexity kind of multiplied by order of magnitude, because now you are not only providing multi-layer networking, it's also need to be divided in different ways, different constraints. So it looks like data normalization across layer and intent interface for upper layer system is inevitable. We as humans cannot interact with complexity of such degree. So obviously, we are working on this technology in IETF. Early start, we started with defining what intent can do for transport network slicing. So there's a draft, again, it's informational, it's for you to read. For better understanding, we are working on it. Please read it, please provide your comments, if any. We are looking for more input to progress the draft. And ideally, we are looking into system that would interact with OSS, BSS layer northbound and IETF network slices southbound that will give us ability to build end-to-end network slicing as well as instantiate different transport slices. And this is very hot topic in IETF today. We are working on technology we have called IETF network slice. So from my point of view, being involved on both sides, I think it's inevitable that there's going to be intent layer to program, to interact, to operate with network slices. So let's move to IBN and its roots. So IBN design philosophy is not how to build network, it's what. The success of the service is defined by successful outcome. So imagine you're building network out of 20 routers. If only 18 of them are working, this is not a successful network. You failed, system failed. So it's very important to focus on what is it you're trying to do and what the end result is, and then going back to get to intended state. Because intended state is really what you want your service to do. So there are more details in the definition drafts. You could take a look. It goes in details on differences between intent-based networking versus policies, how declarative policies are different from imperative, and it's interesting read. So IBN lifecycle is fundamental for system to work. It starts with design phase, which is really intent consumption. Tell the system what you want, express your intent. Could be as simple, I need a path from A to B, could be as complex, I need a service that is point to multi-point across 20,000 devices, and here's 10,000 policies that again are declarative. You're not saying I want IP address A to go to IP address B. From intent perspective, you are saying I don't want HR to be able to talk to engineering or other way around. And it's a role of intent-based system to figure out what it really means. So the resolution of high-level intent into low-level networking concept. Intent modeling gives us ability to build a model of intended state and actually validate that it can be instantiated by underlying network. Still hardware vendor independent. Only on deploy phase, intent instantiation, you would assign your inventory to your intended logical devices. So this is where you would say, this device is going to be Cisco, this device is Juniper, this is Huawei, and then you will associate particular configuration, particular policies with the way particular vendor is doing. When you deploy your network, you need to immediately start validating it, right? At any point in time, your network is not working if you cannot validate it. So the important part here, during design phase, all your validations are defined because you know exactly what your network is going to be doing. Day two operations, you want to change anything, you wouldn't go to deploy phase. You would always go back to design phase to go through pipeline of permutations within IBM. This is mandatory for system to work. Just high-level overview how intent-based system could look like. Even so, it's a perfectly suitable platform for code-based interaction, machine-to-machine interaction. We see most of our customers, they ask for graphical user interface. So really, there is a number of workflow through which user can express their intent easily. Like I want a network that can serve 20,000 servers. That's really high-level intent. So such intent is a model in vendor-agnostic way. For example, if you need 40 servers in a rack, you know you need a device that has at least 40 ports that could be used to connect the servers, and need also number of ports to connect it to the higher level. You also know degree of oversubscription, which is expressed as part of intent, which provides easy ability to normalize this data and provide list of devices, logical devices that could be used to provide this connectivity. After all this data is compiled and modeled, when you know which vendors you are going to use, you are going to configure this vendor in particular way. There are vendors that support netconf. There are vendors that support TL1 only. There are vendors that support CLI. So in multi-vendor environment, in order to address this, you really need to be able to render configuration according to the vendor. And the more vendors you support, the better you can address the market. And based on the combination of intended state and all the telemetry you are getting from the network, you could provide compliance, you could measure performance, you could measure security, you could actually validate that human resources cannot talk to engineering. About 5-6 years ago, when we were writing book with Ross White, we had high hopes the network will become really programmable. So for our ideas about how networks going to look like and definitions. It was also in early days of I2RS. So we really hoped that network and devices will become programmable within a number of years. Unfortunately, it didn't happen yet. So, but network is programmable where both control and data planes provide interfaces to interact with, to read capabilities and program it accordingly to business logic. Interfaces are programmable when they expose capabilities to device, can provide inventory, can provide topology, can provide telemetry. Again, our vision was that it's going to be something generic that today GNMI is trying to do, But we ended up with telemetry provided by GNMI in some cases, topology provided through BGPLS, inventory provided by Excel sheet. So we are still very far. So we have to do something. And it brings us to really need for data normalization. So this fruitcake looks very simple and beautiful. But if you look what it takes to build it, there's a whole bunch of ingredients, some of them to go into the cake, some of them to try the cake, some of them to bring it to right temperature and so forth. Same goes for networking. Unless you can understand the deltas and relationship between different pieces of networking, how do you correlate net flow record to counter? How do you correlate BGP route to FIP? How do you correlate number of VPNs configured to amount of memory available? No, there are many, many things. So bringing all this data, normalizing it, reasonably simple code or human being can look at it and figure out what's going on is mandatory given the complexity of the networking. Architecture goals of IBN are composition decomposition skills. So as we said, networks are growing in size, in bandwidth provided, and complexity of the services. And how to deal with the changes. Even when we plan the change, we spent months planning it, going through board to get all the approvals. How do we know that when we actually change the network, it could still work as desired, that we are still able to meet SLAs after the change? Number two, and even more complex, unplanned change. What if 30% of my network goes down? What if one device went down, but another one up? Do I need to do something? Or maybe I'm still fine. Maybe I'm still within SLAs. So ability to deal with changes at scale is one of the most important problems IBM is tackling. Closed loop validation is another very important point. We are constantly getting more and more data. So thanks to hardware telemetry, again, GNMI, we are getting more and more data. Amount of data that is impossible to store because it's so much. It's very expensive to transport. De facto, you need to build out-of-band network that is larger and more expensive than your production. And amount of noise in the data is huge. You're getting information in which 90% is no use. So you need to get good data in order to afford to get this data. So what you see here is graph database for 10 by 10 clone network with EVP and configurer on top. This is what you need to deal with to understand full degree of all the relationship with the network. So what's composition? We take number of simple function and build more complex ones. Why to use a graph? Networks are graphs, right? Set of nodes and relationship between them. Modern graph structures allow us to run very efficiently queries on them, to walk the graph, to query the graph in real time in order to get real-time answers. Moreover, you could form your query such a way that you didn't anticipate during design phase. So for example, you didn't care about counter for multicast packets. And you didn't care at all. Now you only care on devices that run particular vendor and particular software. Your graph has all the metadata associated with devices. So now you can say, hey, show me all multicast queues on Cisco switches that run NXIS 9.2. All of this becomes naturally available when you build relationship between objects. So we are going to use this very simple model, 4 by 2, 4 leaves, 2 spines, and a bunch of hosts with services in them. So how does it look in graph composition? Spines, interfaces on spines, links connected to these interfaces, interfaces on leaves, leaves, interfaces, links, interfaces, hosts. Very, very simple cyclic graph. But it provides us with so much power and ability to attach metadata to any part of the graph. For example, you might say, my spine are vendor A, while my leaves vendor B. So your question is going to be not show me spine 1 and spine 2. Now you can aggregate and abstract and say, show me all the switches of vendor A. The answer is going to be spine 1, spine 2. And this is just 8, so 2x4 network. Imagine you've got 10,000 of devices and power this abstraction layer brings. Let's take a look at function composition, which is really derived from the graph you've seen. So what you see is exactly the same picture. You've built spines. Your schema defines your data model, so you've built leaves. You've built servers connected to it. You know that spines have to be connected to leaves in particular way because we are talking leaf spine. So every leaf is connected to all the spines in the pod. It's all programmatically derived, very simple. What's interesting now, services are not physical entities. They're ephemeral. They could be configured on any device, connect to any device, and be deconfigured, go down, and many other things. So in this case, we have 2 services that are connected to number of switches. Let's take a look what we can do with it. So this is the resulting model, right? We've got 4 leaves, 2 spines, and 2 services on top. We are asking a very simple question here. Show me all the links that carry traffic from application A to. And walking the graph, it will take you a second to figure out. Imagine if you need to do this manually. It will take you hours, and you're in networks that uses ECMP. You're in network that hashes automatically. So you could do a lot of troubleshooting on top of this. You could do a lot of deviation whether your network state is correct. If you look at next hop, you can figure out whether BGP is working correctly. If you look at EVPN semantics, you could see whether your L2 VNICE have been instantiated correctly. So this is an extremely powerful concept. How do we decompose if we need to drill down? So decomposition is completely the opposite of composition. We take great big problem and decompose it in a number of smaller problems. And I'm going to use exactly the same graph. What you see here is a graphical representation of graph database and the graph query language on the left. So as you could see, it's empty, and we start building network again. Spines, all the links, everything connected to it. So we end up with leaf spine network here and how they're connected. Now, if you want to troubleshoot and see, for example, if all of your links are loaded equally, so we are using ECMP and leaf spine layer 3 networks, right? So figuring out whether they're loaded correctly relative to each other is very important. But how do we know which links should be validated? In this case, it's a very simple query. Show me all the spines, show me in relationship to the spines all the links interfaces and how they're collected to leaf. By asking exactly this question, now I can walk the graph and it will give me exactly 8 links, 4 leaves connected to 2 spines. If one of them goes down, I know exactly I'm losing 1/8 of capacity. If I have more comprehensive network management and I see that one of my link is at 90% and another one at 10, I can go and do something. I could use BGP to inject third-party next hopping route. I could do many things. I could go and kick the silicon to rehash differently. I could do many things, but the answer is very simple. By asking very generic question, show me all the links between all the leaves and all the spines. So you see here 4 and 2. It could be 10,000 and 20,000, but the question is going to be exactly the same. The answer is going to be exactly the same. And last part, let's see how we're doing on time. Great. I would like to talk about intent-based analytics and what they bring. What we mean by intent-based analytics, again, you could read the draft for more definitions. They allow you to extract more knowledge by asking right questions. So imagine if I ask you, how are you doing? Or I ask you, how's your son Paul doing in college? Which answer is going to be more concrete and provide you with more interesting data if you really care about Paul? That's exactly the logic here. We are asking right question, and the question is as detailed as possible to get the most high fidelity data. If you look at a lot of modern networking and actually company, they all, most of them are suffering from hoarding disaster. As a people, we don't do this, right? Usually we try to keep only stuff we need. But if you look at any company, large enterprise, they're sitting on terabytes and terabytes of data saying, you know what, sometime in the future, we will do some magic on it, throw some machine learning, it will give us great insight. Guess what? It's not going to. It costs money, electricity, and compute power. And at some point in life, maybe 5 years from now, they'll just delete all of it. Another point here, it's called Conway's law. All organizations build their software that mirrors the organization. So make sure you are not like this guy. Even if your organization like that, be better than this. So it's a beautiful marketing slide, but the point here, you should only ask for network events that are interesting, that are identified by the service, by your intent. And then you could apply all kinds of techniques. You could compare your operational state to your intended state. You could look at different service techniques definitions. But the point being, you are not asking, send me everything and I'll figure out what to do with it. You are asking network right questions. Let's take an example. So finally, we can get high definition telemetry from our networking. GNMI, there's GTI, hardware telemetry, in-band telemetry, what just happened. So any vendor you go to will give you a different name, but the point being, they can give you hardware-based telemetry that's high definition at millisecond granularity. A lot of data, good data. However, now you're looking at all interfaces on single switch. Now you're looking at all switches, all interfaces. If you're just observing it, we say it's observable. What can you do with this data? Pretty much nothing. It's too much. And you will just incur cognitive debt because you cannot analyze as a human being this amount of data. Forget about asking intelligent question. Not only looking at the graph saying, hey, this graph looks smaller than that one. Probably this switch is doing less traffic than another one. How do you bring business logic? How do you bring context into this question? So very simple question. Is my fabric ECMP imbalance? Meaning some paths are transporting less traffic relative to other one. So looking at 20,000 graphs, probably the answer, God knows. How do you do this with intent-based analytics? Not only figuring out whether there's imbalance, but also bringing context. So from my business logic perspective, in this case, my load sharing is bet only if the deviation is more than 3% and only if it's longer than 3 minutes within 7 minutes. So we ask the question, I would like to see all paths between leaves and spine. So in a bunch of previous slides, you've seen how to do this. Here we can bring business logic saying we need to measure in 7 minutes intervals and see whether at any given point in time within 3 minutes, the deviation is more than 3%. Going through pipeline, only if all the constraints are true, you could notify the user, actually remediate, your fabric ECMP has degraded. Imagine it's less than 3% or shorter than 3 minutes within 7 minutes, you don't need to notify user. From business logic perspective, there are no deviations from intent. This is an extremely important and powerful concept of intent-based analytics. Now you are getting all the interesting events. you could say with 90% certainty it's a cat. However, there's still 10% that could be dog, it could be some other animal. So without understanding the context that came from the design phase, where you define, I've got user A, B, and C, and they've got particular SLAs, it just still a bunch of data, and it could mean different things. Best case, you would guess it's a cat. Worst case, you wouldn't, and you would try to treat it as a cat and maybe kill it, right? So we are trying to avoid not a cat condition. That's exactly what would happen. Imagine there's memory leak on the device. Process that monitors all the processes sees that memory leaks is in routing and kills BGP. Symptoms start to get propagated. Because BGP is dead, you see missing BGP sessions, you see wrong next hops, the whole thing looks different. In fact, your customers are complaining. Something happened, you don't understand why, but your customer is complaining. You try to change, to configure some policy maps. You try to change BGP sessions. Nothing's helping because what you see, those are not the root causes of the problem. Those are the effects of the problem. Your only actionable event is really the memory leak on the switch. And if you can understand, and this is interesting event for you because you know you run routing. If your routing daemon died, probably it's because of memory. At least you know where to look. So when you look at it, you would know, hey, it's BGP. BGP was killed by the monitoring process. Monitoring process killed it because of memory leak. So you will go and replace switch or upgrade or downgrade your software. So rather than trying to dance around the problem for days, figuring out what's going on, you could figure out what the root cause is. And based on root cause analysis framework, you could remediate reasonably quick, not in days at least. We talk a lot about machine learning in networking. So this is really to kind of differentiate between unsupervised learning and supervised learning here. So what you see here is 130,000 sources of data. And by analyzing them, we can actually see that in some cases it's BFD, in some cases interface that's enabled. But this data on itself, and it's a lot of data and a lot of learning, is meaningless because the fact that interface got enabled doesn't mean anything in context of service. So holistic view, while might provide really a lot of data on itself, is pretty meaningless. Macroscopic view is getting interesting changes and then doing reduction clustering. There's a bunch of machine learning techniques to label the data. But the real question here, was I really need to do this? The network, at least in data center, is very, very predictable. We know exactly what it does. So we don't really need to learn. We know from the design phase what it should look like. So point here is really microscopic view is the most important one. Ask right question, choose counter that best describes the state change. Choose monitor BGP session if you use BGP for the services. You use layer to stretch, monitor how your type 3 routes in VPN get distributed. So point here, ask right question. And supervised learning within string constraints and right context is much more useful in networking than just throwing data and hoping that your unsupervised algorithm will find something, and that something is going to be really important. It's not worth it. And really, we are trying to avoid not hot dog condition. This is from a sitcom where the guy invented machine learning algorithm that would look at everything. And unless it's a hot dog, it will say not hot dog. It's not good for networking. We want to know exactly whether it's sausage, hot dog, or something else, or tomato. The fact that it's not hot dog is not good enough. So trying to learn without context will result in exactly that. How do we discover actionable insight. This is an example from my own product. This is stuff I'm working on. And this is really Graph Database Explorer. So what I'm trying to show here is how can you know that something is not working. So we define an anomaly as deviation from operational plus derived and intended state. Intended state, as generated by single source of truth, is per definition what it should be. Operational state plus derived is what it is. So in this very simple example, I'm saying, according to my intent, every switch should have 5 VRFs instantiated. So it's very, very high level query, just showing me all VRFs on every switch. As you can see on output, all the switches that are present in the network show exactly number 5. So I know my intended state says 5, my operational state shows 5. So I'm within the intent, so my network is working as intended. And this query could be really, really complex. There's a lot of metadata in the nodes. You could start extending. You could say, show me all the switches that run version 2. Show me all the switches that have only 40 gig interfaces. Show me all the switches that are only by vendor B. And that gives you ability to monitor your network, to operate your network in such a way that if something breaks, you know not only that something got broken, you know why, you understand the impact, you understand whether you need to do something. So if your network is 30% loaded and you got link down and now it's 35% loaded, do you care? Long-term, absolutely. Short-term, you are still within your SLAs. So you don't need to wake up at 2 o'clock in the morning and do something about it. So this is what context gives you. To finalize, IBA is context-aware analytical framework. It's specified declaratively, so you don't say monitor IP address A, B, and C. You're going to declare your intent. Does my service work? Can HR talk to engineering? Is my service within SLAs as with my customers? It allows you to extract knowledge from a lot of data. Because you're only asking right question and also process it through pipeline, you just drop stuff that's not interesting. And the decision is very simple. It's logical, and if any of components is false, you see an anomaly. If everything is true, there's no anomaly. You want to ask additional question, it's built in. Any metadata that is within the graph could be used. As we said, you could say, show me all the links between leaves and spines, but you can also say, show me all the links between all the leaves and spines that are Cisco. Show me all the links between devices that have 40 gig links, and so forth. So your query could be tailored to your business logic. To conclude, so basic automation, it's really a hot topic. Everybody's talking about automation, Python for network engineers, but the problem is solved. There's a number of ways you could do it very complex. You could do it very easy. You've got open source tooling around it. You can do it. Single source of truth is being implemented pretty much by every system. Anything that's modern uses this concept. What's still significant challenge is really data operations. How do you implement changes without being afraid of breaking your network? And it really provides you with the ability to be agile. Some companies bring 2,000 changes a day to their software. Can you do the same with network? Probably not today, because you just don't know what it does to your network. By being able, before implementing change, to compare future operational state to future intended and see whether it's going to work, provides you ability to bring changes without being afraid. Configuration drift. You've configured beautiful network, but then you have a bunch of people that are going to configure stuff here and there. And as we said, network is a distributed system. Change on one side of the system could result in severe changes on another side of the system. And it's not a well understood technology, not well enough by humans at least. And most importantly, remediate. after you can trust your system to understand what's going on, you can also auto-remediate, which really drives us towards self-driving, self-healing networking. And it's really the most complicated area to drive with because of amount of information, variability of information. Networking really suffers from race conditions, from how protocols behave, how they converge. And we are on the way there. We see good progress. I mean, my company is going to be acquired by Juniper, as announced it yesterday, and it shows that industry understands the complexity and value of the technology. That's all. Any questions?
Thank you, Jeff. Thank you, Jeff. Jeff, we have two questions. See if you would like to answer them. Otherwise, I have
Absolutely.
some as well on the Q&A.
Are you going to read them, or you want me to read?
Now, go ahead.
I need to unshare my screen probably, right?
Oh, no problem. I'll read it then.
Okay.
Google has recently published a network model called MALT. Are there any other network models proposed inside IBM?
So there are no publicly available or open source models. There are very early open source tooling such as Netbox, some others. So both been around for, it's not a new work. It's been around probably 7, 8, 10 years. So there's thousands of man years that went in. I think in ATF we will try to work more on this because now we are just starting. So we just finish definition work that defines what IBM is. Definitely not what it does, how it works, and data models for it. So you won't see anything open and working today. But my hope, and I personally very involved in this work, we will work in ATF and some other SDOs on providing more and more data, helping people around to use what we have created.
The second question is from Samar. How intent can match to configuration of network and devices? Are there some predefined configurations? And how
Very
to
good
define
question.
new configurations based on intent?
So the fallacy is that you use configuration as source of truth, which is wrong. You shouldn't. Configuration, while on most devices today it's a text file, it's an ephemeral thing. It comes and goes, and you should treat it such way. You should never have conflict between your intended state and configuration. If there's a delta, single source of truth always takes precedence. So if someone went and configured some change on the device, my system would flag and say, hey, look, there's some delta. What do you want to do about it? In most cases, I'll just revert to known state according to intended state. Because if I don't understand what you have configured, we just got out of sync between operational state and intended state. So practically, there is no competition. The intended state always takes precedence.
Jeff, if I want to add on to this question, basically sometimes what many programmers, or at least people in us vendor companies, always are coming up with new features and new command lines, new things on our devices. So many people get confused that, oh, how would I go and update my intent system when there is a new feature that comes in? And would I need to overhaul everything? How does that work?
So there's theoretical consideration, practical. A theoretical one, I've got data model, so I just change schema and extend it to new feature. Practically, there's always additional work, and unfortunately, different vendors do different things. Since intent-based network system is vendor independent per definition, eventually you would need to implement same feature in different ways in different vendors. We see a lot of the stuff in the VPN. So practically, how we do it, if it cannot be quickly integrated into schema, into graph database, you would use something we call configlet, which is just piece of text you would go and configure. So you understand the context, but it's not properly modeled, which is temporary situation. So eventually, this piece will be integrated into main system, main database, and become first-class citizen. But it's a very good question, and it's situation in the field. What's also important is, people like building snowflakes, so there's absolutely no need. So having intent-based system brings discipline. You build a pod and it's working. When you're going to build second, third pod, you're going to build them in exactly the same way, because it's much simpler to just copy blueprint you created once than reinvent the wheel every time. So you won't see this kind of dispersion of features doing same thing in different ways, because this workflow of intent-based system wouldn't allow you to do it. It would always give you same result if you provide same input. So idempotency is one of the very important attributes of an IBN.
Let me ask one more question, Jeff, but other way around. Are most of our intents would be well known and well defined by our systems, or is it like we are making some building blocks and we would let the operator use those building blocks to programmatically come up with new intents for our systems as well?
So it's
Which
important.
approach is most
Yeah.
common?
Most common is to use common building blocks. For example, if you're in data center, in most cases, you're going to use EVP and VXLAN for segmentation, multi-tenancy, and BGP for underlay. So there is no reason to, there's some difference. You could use V4 or V6, which is really, you shouldn't really care what you're using, right? System will take care of it. You could use layer 2 only or layer 3 only. But again, you express at reasonably high level. So you don't know the difference between vendor semantics. You don't need to know. When you express your intent to the system, it's role of the system to say, I'm going to configure Arista in this way, Cisco in that way, and I'm also making sure that they're going to interrupt. And this is work that needs to be done by the company, such as mine. We run 10 million tests a day on our CI/CD pipeline. So when we ship a product that supports particular features, we guarantee that stuff is working. And I mean, it's not sexy. It's a lot of work, hard work, but this is how you make whole system work.
Jeff, there's
on one side, there is intended state. On another side, there is reality, bugs in software, bugs in hardware, and you need to figure out the stuff is actually working, not just theoretically.
Perfect, Jeff. Jeff, one question from Vijay. What would be the intrusiveness of IBN on the performance metrics of the network? I'm not sure I completely follow, but maybe you could have a better thing. Vijay, would you like to clarify a little bit? I'll allow you to talk as well if you want. Intrusiveness of IBN on performance metric of the network.
Yeah, is it okay? Can you guys hear me?
Yeah.
Yes.
So I was just wondering if all of this telemetry and system information gathering is happening on a real network and feeding towards a remote system to actually give some intent-based reports, right? So is there any intrusiveness? Because I'm sure that when you're collecting all the system statistics and telemetry, there could be some intrusiveness in packets per second, latency, and jitter.
Okay.
Absolutely. It's a great question. So how do we reduce impact of asking more and more questions on the devices? Number one is asking right questions. So you're not asking, give me all the data you've got, give me all 50,000 counters you hold. You're asking only for information that's important to your services and in context of the services. Number two, you need to do first degree of aggregation as close as possible to the device, ideally on the device itself. So we see the streaming telemetry. Now you've got ability to trigger transfer of data conditionally. So for example, only if particular counter increases by more than 10%, let me know, otherwise I'm not interested. Same could happen if you could install piece of software and switches, which we do as a company as well. And I will analyze raw data that's coming in, aggregated. For example, rather than streaming changes, I'll provide deltas every 5 seconds rather than doing it every 100 milliseconds, which is meaningless if fidelity of the service doesn't require it. So you always need to bring context and what's expected by the service versus how you're gathering the data, how often, fidelity, timing, and this kind of stuff. So you are not trying to kill the system. You are trying to ask as much as needed to validate that service is working as required.
Thanks, Jeff. Really informative. Thanks for a great session.
Thank you. Appreciate it.
So thanks, everyone. That was our last talk from Jeff. We are done for the day. We have the social link. If any of you would like to get on it, I will be there. If you want to socialize with other attendees, this will be a good way to do that. And let me just give a quick introduction for tomorrow's track as well. Tomorrow, we will be talking about transport. It's on the same time as today. We have a talk from Jenna, who was involved from the start of Quick work. So it will be a good to get an introduction on Quick from Jenna. And then we have Mohit from NITK and Professor KK from University of California talking about congestion control. So again, a great set of talks. We have not done transport area before in Connections. So it's good to give transport its due. And I hope you guys will join tomorrow as well. Thank you. Have a great day or a great night wherever you are. Thanks. Bye-bye. Bye, Jeff.
Bye. Thanks. It was really great.
Bye.
Thanks. Bye.